In this video, we're going to be introduced to something known as implicit differentiation. When we take the derivative, usually y is by itself on one side of the equation. But do we have to get y by itself first? Let's figure that out by taking a look at this example. To begin with, let's take the derivative of 2x squared. So we'd have 4x. The derivative of a minus x is minus 1. And the derivative of y we write as dy dx. And then finally on the right hand side here, we'd have the derivative of 3x to the fifth, which would be 15x to the fourth. Do we get the same answer if we take the derivative over here? Well, let's see. 3x to the fifth would be 15x to the fourth. And then if we take the derivative of a minus 2x squared, we'd have minus 4x. And then we'd have plus 1. Now these might not look like the same answer, but notice that if we solve this equation on the left-hand side for dy dx, that we actually do end up with the same answer. 15x to the fourth minus 4x plus 1. Here we could have easily solved this equation for y, but sometimes it's a bit more challenging to solve for y. For example, here it's actually impossible to get y by itself. So how do we find the derivative? Well, if you take a look at the back of your notes, you'll see that I've listed some steps for differentiating implicitly. The first thing we do is differentiate both sides of the equation with respect to x, or whatever variable is involved in the equation. If we run across an expression that involves y, we write the derivative of y, which is dy dx. Then we work to get dy dx on one side of the equation and isolate dy dx by using division after we have factored out dy dx. This will make more sense as we work through an example. To begin, let's start by taking the derivative of y cubed. And you might say, well, I thought we can only take the derivative of x. Well, to take the derivative of y cubed, we're going to have 3y squared, but then that was the derivative of y with respect to x. So we'll have 3y squared, and we'll write dy dx. So essentially, whenever you're taking the derivative and we're working with y, you'll write dy dx. So 3y squared dy dx. And then we need to use the product rule to take the derivative of the product of x squared y to the fifth. So we have the first function times the derivative of the second function. So the derivative of y to the fifth is 5y to the fourth. But we took the derivative there with respect to y, so we write dy dx. So that's the first function times the derivative of the second function. So that's x squared times the derivative of y to the fifth. Then we have the second function, which is y to the fifth, times the derivative of the first function. So that's 2x. And then we finish up by taking the derivative of the remainder of the equation. So we'd have 4x cubed. And then the derivative of 27, which is 0. The next thing we would do is get dy dx on one side of the equation. So in other words, I would move the 4x cubed to the right and the 2xy to the fifth also to the right. The next step will be to factor out the dy dx components here. So you can see I've done that. So I have dy dx times 3y squared plus 5x squared y to the fourth on the left side. And then finally, I'm going to divide both sides of my equation by 3y squared plus 5x squared y to the fourth. So my derivative is 4x cubed minus 2x y to the fifth all over 3y squared plus 5x squared y to the fourth. These are a little bit challenging and they will take a little bit of getting used to. Let's take a look at how this particular derivative is applied in this problem. So we've taken the derivative of this equation already, and we're going to find the slope of the tangent to the curve at the point 0, 3. So notice that this is our x-coordinate, and this is our y-coordinate. So wherever I see an x, I would substitute in a 0, and wherever I see a y, I would substitute in 3. However, notice right here, this part is going to be equal to 0, since we're going to have 4 times 0 cubed, and this part's also going to be equal to 0, since we'd have 2 times 0 times 2 to the 5th. So our numerator just ends up being 0. I don't really care about the denominator at this point, because I know if the numerator is 0, that my entire fraction will equal 0, and I know the slope of the tangent at this point will be 0. In other words, we have a horizontal tangent at the point 0, 3. Let's just confirm this by taking a look at this equation in Desmos. So here we can see I've entered the equation in Desmos, and here's the point 0, 3, and you can see that we in fact do have a horizontal tangent at the point 0, 3. The slope of the tangent line there is 0. And this is not sharp and pointy. There actually is a derivative that's defined at that point. Let's take a look at one final example where we have the equation of the circle, and we're supposed to find the equation of the tangent line when x equals 3. So let's begin by taking the derivative of x squared, which is 2x, and the derivative of y squared, which would be 2y dy dx. And notice I have to say dy dx because there I'm taking the derivative of y with respect to x. So whenever we take a derivative involving y, we write dy dx. And the derivative of 25 is 0 since 25 is a constant. Next, I'm going to solve for dy dx. And when I solve for dy dx, I would subtract 2x, so move this over, subtract 2x, and then divide by 2y. And I would have negative 2x over 2y, which simplifies to negative x over y. So the slope at any point on our circle is the opposite of the x-coordinate divided by the y-coordinate. Well, I have an x-coordinate, but I don't have a y-coordinate for a point here on the circle. So let's solve this equation to get our y-coordinate. So I'd have 3 squared plus y squared equals 25. And actually, there's two different solutions here for this. I end up with y squared equals 16, and that means y is either positive 4 or negative 4. So actually, I have two different points on this circle that have an x-coordinate of 3. One of the points is 3, 4, and the other point is 3, negative 4. So when this equation asks us to find the tangent line when x is 3, there's actually two different tangent lines. This particular tangent line would have a slope of negative 3 over 4. That would mean that its equation would be y minus the y-coordinate equals our slope times x minus the x-coordinate. So we'd have y minus 4 equals negative 3/4 times the quantity of x minus 3. That's one of the tangent lines. And our other tangent line would have a slope of negative 3 over negative 4, which would simplify to a positive 3/4. So the equation of this other tangent line would be y minus a negative 4, which is the same as y plus 4, equals 3/4 over x minus 3. Let's take a look at this one in Desmos as well. So there's our circle, and you can see I have the point 3, 4, and here's the equation of its tangent line, and I have the point 3, negative 4, and here's the equation of the tangent line at that point as well. We'll be doing several more examples involving implicit differentiation over the next couple days, but hopefully you'll be able to do a few of these problems on your own for homework tonight.